Hey guys, I hope it's going well. This is our last lesson for this unit. So you'll have a mock test in place of a real test, and you can see how it goes. And then you'll have an assignment that will be graded. But let's just go through this last lesson. This one actually isn't in the textbook, but it's a valuable lesson because if we didn't talk about it, you would just probably think that everything can always be matched by a straight line, which just realistically isn't the case. So this one's entitled Nonlinear Regressions. And it's pretty neat because your calculator has everything on it in order to do these calculations for you and figure out whether or not you have relationships that can be modeled by other types of curves rather than straight lines. So like exponential, quadratic, cubic, quartic, a whole bunch of different things it can do. So in real life, a lot of things won't match linear, as I said. If you look at the COVID-19 stuff right now, obviously, those are being modeled by things that are exponential or logarithmic in some cases. And so the way to figure out what's the best equation to do this is use what's called the coefficient of determination, which is similar to what we had for R, which was the coefficient that we were using to match which was the strong positive or negative, related to lines. And this one, it's kind of like a curve of best fit. And the math that goes along with this is quite complex, which is nice that it's on your calculator so you don't have to really worry about that. Which basically it's measuring how closely a curve fits the data. And so sometimes you don't even need this calculation. Like you can just look at the data you have and see if what's going to match. Like for here, I've got this data that's going up like this, which isn't really a straight line. And similarly, this is the same data. This curve that they've got obviously doesn't really match that. Whereas this quadratic does match it. Obviously, you would restrict the domain. Whereas this thing, I think this is another exponential type thing, it doesn't match it. And so you can go through, you can try to do this either by eyeing things up and trying to figure it out, or you can use this R squared. And so what's nice about having a curve of best fit or line of best fit is that it allows you to extrapolate for the data, just like people are trying to do, or health professionals are trying to do right now for the COVID-19 stuff. They're trying to extrapolate how things are going to look within, a couple weeks based on data they're looking at from other countries and making comparisons. And that's why it's not an exact science. They're coming up with values that are between pretty large ranges of numbers. And so they use these models in order to try to figure this out. And some of it is matched up by this kind of thing. Okay, let's take a look at an example. I think that's kind of interesting to do, and that's looking at the number of confirmed COVID-19 cases in Ontario and the respective dates here in this table. So I just picked from March. So this is the data from the provincial website, but I picked from March 19th all the way to April 1st. So I've done 14-day span up until April 1st, and these are the number of confirmed cases. There's one thing to note. If you scroll along here, note the number of confirmed cases didn't change for 2 days. So what I'm going to do is I'm going to cross out the second day because it's kind of like this outlier. I don't know if the government took a day off from its confirmed cases, but let's just cross it out. This still will be whatever day it is, and then we'll jump a day to the next one. So it's still 14-day span. So what we're going to try to do is to find some sort of relationship, curve, or line of best fit that matches up with this. And so first thing we're going to do is create a scatter plot, and we'll classify the linear correlation. So if we look at that, so the first thing you need to do is go to Stat, here in red, press 1 or Edit, Enter, and you can put in their data for L1 and L2. So notice as we go along here, in L1, these are the number of days, so there should be 14 days, but what I've done is I've deleted day 10, which is the one that had 993 a second time. So there's a jump here from 993 to this, but that's because it's really 2 days. So I've cut that outlier out. So that's important to note. So in order to create a scatter plot, so if you need to, press pause and on the video, and then you can input this data. So in a scatter plot, we're going to go second function y equals. And you can go to number 1 and turn it on. I've gone to number 2. It doesn't matter which one you go to. So you have to scroll on to, so this is how it might look for you, but I'm going to put it on. So I go to on and press enter. And we want our X list to be L1 and our Y list to be L2. So once that's on, it will plot that. The only other thing we need to change is the window setting. So if you go to window, what we need to do is have it go, if this is day 0 or day 1, 2, 3, all the way to 14, my X values are going to go from 0 min to max, I'm going to say 15. It's generally good to go a little before and a little after what your numbers are. And your scale is the number of ticks you'll see, or the rate at which the ticks are. So this is going to be every 2 units. My minimum, I'm going to go from 0, and we're up to about, at this time, 2392 cases. So I'm going to go up to about 2500. And my ticks will happen every 500. So then once you've got that, you can just press graph, and we get this. So I'm going to copy this into my note. So we get this kind of correlation. Pull it down here. And it says classify the linear correlation. So in order to do that, we have to go again to stat, and we go to calc, and we want a linear regression. So I go to linear regression, I press enter, and it gives me this information. I need to calculate it. So I press enter, and I get this information. I'm going to copy this in. So this is my linear regression. Get that. And so it says classify the linear correlation. So I'm going to answer that here. So if you look at here, my R value is 0.955. That's a pretty strong positive correlation, although linear. So it says determine the correlation coefficient. So that's that value. So R equals, little r equals 0.9, I'll just round 55. And then the new thing we're going to use, which is the coefficient of determination, which is R squared is equal to 0.913. So again, that R squared measures how closely the line or curve models the data set. So we get that. What I'm going to do in the next one, it says add the line of best fit to your scatter plot. So I'm going to put in this line. So if I do that, I go to y equals, and I think oh no, I don't have it typed in right. So I've got 154.14007, and that's times x, and then minus 171.125. That one's less important because it's just the y-intercept. So now when I go to graph, we get this line. So I'm just going to copy it, and then we'll discuss it for a second. So if you take a look at this line of best fit, oops, where'd that go? Pull it down. So there's my straight line. And if you look at it, most of the data is like pretty close to the line, but why this is not a good representation of the data? The reason is it doesn't model where the trend of the data is going. If you were to think of extrapolating data below this line, you would end up with points down here rather than points of where this curve is going. Similarly, on the right side of the equation, if I was to extrapolate data using this straight line, I would end up over here somewhere instead of up here. And so we can say it is not a good representation because the line does not follow the trend of the data. And so it would not be good for extrapolating data. So even though we got a pretty strong positive correlation, it doesn't necessarily mean it's a good fit. And so if we were in class, we would discuss this, but are there other functions that may be a better fit? Yes, of course there are. So that's what we'll put in here. Yes, of course. So what we're going to do is perform a bunch of different regression analysis using your calculator. And as I said, it's got this built into it. So first one we'll do is a quadratic regression. So it's pretty easy to do. So if we go back, press Stat, scroll over to Calc, and we're going to go down to number 5, which is quadratic regression, and press Enter. So then we go through, press Enter on Calculate, and we get this. So I'm just going to copy this, just so we have it. But we want that r squared value. So I'm going to put that in here. So notice I get an r squared of 0.9949. It's a very strong representation. So let's see what else we get. And we're going to use this r squared from each to see which one might be the best. So if I do a cubic regression, again, go back to Stat, Calc, and go down to 6, which is cubic, press Enter, and obviously calculate that one. And we get this one. I'll put that in, oops. So this time I get an r squared of 0.9989. And notice all these values here. We've got cubic regression of ax cubed plus bx plus cx plus d. But it's really the r squared in this point that we want to find out if it's the best representation. So if you compare it, they're very close, but this one obviously is going to be a stronger correlation between the two. So if we go to an exponential, again back to Stat, Calc, and the exponential is beyond number 9, so you got to go down below. And so you'll see it there. So I'm going to press Enter on exponential, calculate, and this is what we get. So exponential equation being a times b to the exponent x, where a and b are just values determined by what you've got in this equation. So in this one, I get an r squared of 0.9989. So this is actually pretty much the same as this cubic one. But I'm going to stick with the exponential because I think it's going to be a better match. But they're essentially the same. So it says use the coefficient of determination to determine which model is best. Well, really, the cubic or exponential regressions have very strong correlations based on r squared. So let's go with the exponential though in this case. So it says use the appropriate equation to represent, and we're going to extrapolate beyond and see how good our model is, because as you noted, I only picked days up till April 1st. We're now on, what is it, April 6th. So let's take till yesterday. So April 5th, which would be day 18 in my model. And then we can see up till April 30th, which the government has come out and talked about what the values or the predictions might be. So what I need to do is I've got this equation. So the equation is y equals 218 point, and we're going to use all of these numbers, 0.42353 x, times, so I'll use a star for times, and then my base is 1.184427, and so on, 6. There we go, and that's to the exponent x. And so what this base is representing, if you remember from your other math classes, this means that the number of cases is increasing about 18% per day on average. And that's what this is representing. And so if we take this, I want to figure out how much it would be on day 18 and day 43. So if I get out of here, I'm going to type those in. So I just need that equation. So y, so I got 218. And you can try this yourself. That's times 4427, and that's to the exponent x. Only in this case, we're going to make x, what did I say, 18. So that's going to be as of yesterday, and we'll see how accurate our model is. And so what we get is 4,588, so which is pretty decent measure. If you compare that, that's actually, I think yesterday we were at just over 4,000. So our model is a bit higher than what they've got based on this equation. So even today, I think we're at 4,300. So we're a fair bit above where we would see it. The other part here is to estimate on day 43. So I'm going to take this equation, I'll repeat it, but I'm going to change this to 43. Oops. So we'll try that. Wow. So that means that this is estimating that this is 315,000 based on that. So I'm just going to put that in there. I don't know if that went away. Oops. If I can put it here, I might have to pull it down. Sorry about your eyes. Yeah. Let's just pull this down. So we get values here of 315,000, which is quite a bit of a, hopefully, overshot of what's going to happen. This model predicts, or predicted, 4,588 cases on, maybe I should round that to 9, on April 5th, and 3,015,797 on April 30th. There were actually, I don't know if I have it available here. Let me see if I do. I don't think I do. I think it was around actually 4,038 or so, something like that, on April 5th. The government is predicting a max of, I think it's 80,000 cases by April 30th. So you can see how this changes quickly. And I think if we had have taken data all the way up until yesterday and then try to predict, we might get even better results, or closer to what the government is predicting. But you can use this, it's pretty powerful stuff in order to create, especially when you get these models that have an R squared that's so close to 1. And so what I'd like you to do is two things. I want you to do something similar to what I just did. I want you to pick any 14 days for any place. It could be in Canada, it could be Canada as a whole, it could be a different province, it could be a different country, but I want you to take 14 days of data and find the best model and get an equation like this, and then see if you can predict how many will be on April 30th, and so that you'll be able to check your estimate for that location. Again, so you're going to take any 14 days consecutively from any location, get a model, put it in your calculator, and get this equation, and then see what comes up with. So you can do that, plus there's a short 1 to 3 on a handout that I'd like you to try. And so I'm just going to put this in just to show you the equation. Oops, if I type in the exponential equation that we had, just so you see it modeled. So the exponential equation here is 218 and that's times, and b is 1.18, and then to the exponent x. So I'm going to plot that and see what it looks like on my graph. Yeah. So you can see it's almost perfect, slightly off there. That's a pretty good model, but we start to differ in that last day, it looks like. I'm just going to put that on here if I can. Oops. I don't know if it'll work. Anyway, you get the idea. You can put that onto your scatter plot. Here, so pretty cool stuff to be able to do. So again, I'll type in those instructions for the homework. Okay, take care.